This is Chapter 2, Matter and Energy. In Chapter 2, Section 1, we start off by looking at chemical energy. Now, chemical energy is just the energy that exists in the bonds that hold atoms together. And when those bonds get broken, that chemical energy can be released. So, for instance, like when we're chewing up our food and digesting it, we're breaking the bonds that are in that food, and that will release the energy to our bodies. Energy is the capacity to do work. The units that we will measure them in are joules, which are represented by a capital J. We might also use kilojoules, which a kilojoule is equal to 1,000 joules. One law that we'll be looking at is called the conservation of energy. And anytime something is conserved, that means that we're not creating it or we're destroying it. So with the law of conservation of energy, energy doesn't just magically disappear, nor does it magically get created. It has to go somewhere. Mass and energy are closely related. You're probably familiar with the equation E equals mc squared. Okay? E stands for the energy. In joules or kilojoules, m is going to be the mass of an object, and c is going to be the speed of light, which is 3 times 10 to the 8th meters per second. So because of those units there, kilograms for mass and meters per second squared, that will be equal to kilograms meters squared per second squared, which is what 1 joule is. They are equivalent to each other. So 1 joule is also 1 kilogram meter squared per second squared. And this equation, E equals mc squared, just simply relates how much energy can be obtained from a given mass. So if you have mass and you always have speed of light, since it's a constant, we can calculate out how much energy that we can produce from that mass. If we had the amount of energy, we always again have our speed of light, we could calculate out how much mass had produced that amount of energy. There are a couple different types of energy, the first being kinetic, and that's just energy of motion. The faster an object moves, the more kinetic energy it will have. And to find kinetic energy, you're going to need mass and velocity. This is our equation here, 1/2 mv squared, where mass is m and v is velocity. Another type of energy is potential energy, and that's energy of position or stored energy. So there are different types of energy that things can be converted to. Energy can be transferred. Okay, so it's not created or destroyed, but it can be transferred to different forms. The most common form of energy transfer is through heat, and heat is the total kinetic energy of all of the particles in a particular sample of matter. And this is just a little refresher on system and surroundings. Remember, all the components that are being studied are going to be making up your system, and then everything that surrounds that are the surroundings. So when you have heat being transferred from your system out into the surroundings, that would be an exothermic reaction. You will need to know the difference between heat and temperature. Okay, so heat was the sum of all of that kinetic energy in a sample. Temperature basically tells us how intense that heat is. It's going to be an average of the kinetic energy of the particles in a sample of matter. And we will generally use Celsius here in this class or Kelvin. We will be converting back and forth between these scales. For Kelvin, if you take the temperature in degrees Celsius and add 273.15, that will give us our value in Kelvin. Now notice there's no degree symbol with Kelvin. You simply say a certain number value and Kelvin, no degrees. And this is where you have absolute zero. Absolute zero is 0 Kelvin, and that is the lowest theoretical temperature you could possibly get to. And that means that there should be no molecular motion whatsoever. With Celsius, if you have Kelvin, you can subtract 273.15, and that will give you your temperature in degrees Celsius. If you have Fahrenheit, you're going to need to subtract 32 and then multiply by 5/9. And then the opposite, if you're trying to get Fahrenheit from Celsius, you take your degrees Celsius, multiply that by 9/5, and then add 32. That will give you your temperature in Fahrenheit. The next thing is specific heat capacity. We're just going to do a little bit of an introduction here. We'll talk more about this in the thermodynamics unit. But specific heat capacity is represented by a C with the subscript P. And it's just the amount of heat energy that's required to raise the temperature of 1 gram of a substance by 1 Kelvin. So essentially how much heat that something can hold before its temperature will change. So the units are joules per gram Kelvin, and these values can be calculated from experimental data. Okay, so you could calculate this out in the lab. There's also some tables in your textbook that can give you values or specific heat capacities of various substances. And this is one of the reasons why, like say you're making a cake or brownies at home, and you might see on the box that it says if you're cooking in a clear glass pan, bake it at this temperature. And if you're using a dark colored pan, then cook it at a different temperature. And that's because those pans have different specific heat capacities. So they can hold heat differently, and it will cook your food differently.